atoms, molecules, and ions. This is where we get into the atoms, atomic structure, and we end in naming. Chapter 1 and Chapter 2 will be on the first exam, and probably part of Chapter 3 for the summer. For the fall, if we're online in the fall, not so much. But just look at the study sheets for that information, specifics. All right, just to get us in the big picture, people have been thinking about the structure of an atom for years. Democritus was a Greek philosopher, and he was the first one to theorize that you couldn't keep cutting things down. At some point in time, you would no longer have what was an element. So he said that at some point in time, you reach a point where if you go below that, you do not have the element. So the matter would no longer exist. He called these small indivisible particles atomos, meaning indivisible, and that's where we get the phrase atoms. And so when you look at different things, now with modern technology, we can actually use an atomic force microscope, which actually has a single atom at the tip of it, which allows you to go across the surface of an element, a molecule, a compound, whatever, and get the structure for it. So this is the structure of silicon using an atomic force microscope. It works like an old LP record player. All right, that brings us to, we've got to get our laws together in order to discuss the atoms, the first in compounds. The first one is the law of conservation of matter. That means that the total mass remains constant or the same. And this is, where does it remain constant? During the chemical reaction. So when you start, if you have a particular mass, like 220 grams, then when you're done, you may have different species, but you still end up with 220 grams. So it's the law of the matter stays constant. Okay, so another way to say that is that in a chemical reaction, atoms can neither be created nor destroyed. Okay, they can only be converted into different compounds. So when we talk about chemical reactions, what we're going to talk about is rearranging the species in them. So the law of conservation of mass or matter is similar to the law of conservation of energy. You can't create nor destroy, you can only rearrange, reorder, and the mass is constant. All right. The other concept that's really important when we start talking about compounds is there are compounds of that elements can combine in different ratios. So each particular compound has to have the same composition. So this is the law of constant compositions. So that means that all samples of a compound, the same compound, must have, pound. Yeah, if I could spell, life would be easier. Must have the same composition. That means it must have the same number and type of elements. So what that means is that if we're looking for carbon monoxide, then we're looking at it as 1 gram of carbon for every 1.33 grams of oxygen. Now, some of you are going to look at it and say, well, why don't we say it's 1 atom to 1 atom? You can say that, and that is also true. However, at the time that these laws were written, they were not able to get at the atomic level. They were only able to do it in grams, so it's done in grams. So basically, they have the same composition. Okay, and in this case, the gram ratio. As I said, we know that number and type. Okay, the law of multiple compounds says that in two or more compounds, and there are a lot of them, of the same two elements, or more elements, because once we get up, we can get more. The masses are combined in a fixed rate number ratio. And they're different for different compounds. And they're different for different compounds. Okay? So, an example of that is that for CO, which we just saw, is 1 gram of carbon per 1.33 grams of oxygen. Whereas for CO2, where we know we have 1 carbon for every 2 oxygens, we have 1 gram for every 1.66 grams of oxygen. Okay? So, again, for the same compound, the ratio is the same. So what this means is that we have to combine in fixed ratios, and if we have the same elements combining to form two different compounds, then they have to have fixed ratios, but the ratios must be different. And this occurs with 2 atoms, 3 atoms, 4 atoms, and on up. So we can have totally different compounds. So we had Proust's law of multiple proportions, and the first law was Lavoisier. And let me go back and put that in. There's Lavoisier, because at some point in time on this test, you may be asked to identify people and what they contributed. You don't have to worry about the dates. I put the dates in so that you have a frame of reference, but worry about the names. So if I say who was Lavoisier, you can say that he was the guy who came up with constant composition, law of conservation of matter. Whereas Proust, whichever pronunciation you want, is the law of definite proportions. So as we go through, we'll look at a lot more people as we go. Now, the next guy to come forward was John Dalton. And John Dalton gets a lot of credit for things because what he did was he took Lavoisier's law and Proust's law and a lot of the other reigning theories of the day and combine them all. Now you have to remember that back in the day when this was going around, the late 1800s, early 1900s, early 1800s too, you didn't have the internet. So if you sent something out to somebody via mail, it might take you 6 weeks to 8 weeks to even get a response. So things were slow, so combining things was actually a really good thing. And that's what John Dalton did. And the first thing he stated was that all matter is composed of tiny indivisible particles called atoms. He got this from Democritus, which is atomos. So that is the smallest particle. All atoms of a given element have the same properties. Doesn't matter whether you're dealing with gold in the United States, Korea, England, Germany, doesn't matter. It has to have the same properties or it's not the same species. This is always one of my favorites is atoms of different elements have different properties because if they were the same, it'd be the same element. Compounds are formed by the combination of different atoms in fixed whole number proportions. Okay? Now, this is taking Proust's rule from the grams into the actual atoms. And a chemical reaction involves the joining, separating, or rearranging of the atoms. And again, this is constant mass because you're not creating, this is the law of multiple proportions. Portions, I can't spell. Okay, because you're not making anything new. So what Dalton did was he put a lot of things together in his atomic theory. So a lot of times you'll hear about Dalton's atomic theory, and yes, he gets credit for putting it all together, but he did pull from other things at the time. All right, so since we're trying to talk about atoms, we're going to talk about some other things that were going on along the time that they were producing the atomic arrangements. And the first one is Michael Faraday. Now, you will encounter Michael Faraday again if you take 1212 in chapter 20 because he is the father of electrochemistry or electricity. And so he came up with the passage of electrons between metal plates, and these were important because they were able to use these to further study the atoms, and he called those cathode rays. Now, William Crookes was the one who developed an electric discharge tube. I'll show you a Crookes tube coming up, and that allowed them to actually study the cathode rays. And those have been modified to produce cathode ray tubes, and the T is in there, but they're called CRT. And the CRTs are what the original monitors on computers and TVs were made of. If you have access to an old TV, non-LED, the really big ones that are really deep and kind of crackle, if you put your finger on it, you can actually see the electrons, which are creating the image, follow your finger. Okay, so this was again in the 1838, 1879. Now the Germans proposed the rays were a form of light, and the British proposed the rays were particles. Now you may be wondering why the Germans and the British were involved. Well, guess what? This was World War I started around the turn of the 1900s. And guess what? This was the leading thing in science. And when you have something on the cutting edge, somebody's going to want to use it for war. And that's what they were doing. But in 1898, J. Thompson, you're going to see him a lot, proved the rays were particles. And we'll take it a step farther. And what he did was he measured the mass to charge ratio of these rays. And he was able to find the value. It's given right here. You do not have to memorize it nor know it. This is a cathode ray tube or CRT. And what he was able to do was measure this. And he determined that there were some unique properties to the cathode rays. And so we have to look at those. The cathode rays were emitted from the cathode, which is positive, and travel to the anode. So they're going through the tube. They travel in a straight line. And they knew this because what they did was they put an object in the pathway so it created a shadow. So they were able to see that these whatever they were, these particles were creating a shadow. Now, they cause either the metal or the glass, whichever they're in, to heat up. So they knew that it was giving off a lot of energy. And they called some of the gases to fluoresce. This is where we get fluorescent lights from. They were deflected by magnets. They were toward the positive. So in this case, the cathode. Oh yeah, this is opposite. This is an electric thing. So the cathode is negative and the anode here is positive because it's an electrolytic. I just finished doing electrochemistry. Okay, so we're towards the positive pole, away from the negative. And what that tells you is that it is a negative species because it would be attracted to positive and deflected from negative. And what they found is it was independent of the cathode material. So it didn't matter what you used for the cathode, you would get the same thing, which meant that it was common to all metals because they were using metals as your cathodes. So they knew that this was a particle. They knew it was a beam. They knew that it was negative, and they knew that every species had it in common. Okay, so that brings us back to Michael Faraday, who worked on electrolysis, and that's where he worked on the electricity, the ability to produce electricity, etc., and move them. In 1874, George Stoney, who was a grad student, he's proposed that these things were the fundamental unit of electric charge, fundamental unit of electric charge. And he was the one who got to name it. Guess what he called it? An electron. So he determined that these were electrons. So cathode rays were composed of electrons. And as we know now, they're the same in every any element that you put is you have electrons. Okay. Now remember, J.J. Thompson got the mass to charge ratio. Robert Millikan and his famous oil drop experiment, basically how it works is he was able to atomize the oil droplets and they pick up an electric charge, and he was able to float them in between two plates and with the x-rays determine the charge. So what he was able to do was determine the charge on the electrons. Well, remember, J.J. Thompson had the mass to charge ratio. Millikan has the oil drop. So he has the charge, so they were able to calculate the charge, the mass of an electron. And if you notice, electron masses are teeny tiny. Atoms are small, but they're even compared to one of the other units, electrons are tiny. More about that later. So, again, we're still trying to determine how the atoms are arranged, and so we get into the radioactivity. Okay, again, the dates are there to give you the frame of reference, but you're responsible for the names. Okay, Röntgen discovered X-rays. Now, we use X-rays all the time to take pictures of your bones, but at the time, Röntgen was one of the first ones who was playing with radioactive materials, and he discovered X-rays. Becquerel discovered uranium salts, and that allowed him to do a variety of things and determine that some salts, metals, etc. will give off radiation. So he's kind of the father of radioactivity in terms of looking at it. Ernest Rutherford described the alpha particles and the beta particles, and they were used heavily in determining, and I'll go over exactly what those are in a minute, but that's a beta particle. And then Soddy and Ernest Rutherford were able to figure out radioactive decay. What they figured out was you could take a species that is radioactive, and over time it changes and it goes down in terms of the radiation, but as part of that, it changes the compound. Whether the compound is a molecule, an atom, etc. It's usually an element. So it's actually changing structure as it decays. And so that was Soddy and Rutherford. The types of radiation are simple. You have gamma rays. These are high energy rays, and they will pass through solids. And I always tell people that the Japanese are studying these, and they're studying them by digging underground, and they have these vats of substances to capture the gamma rays once they come through. They're going to pass through solids easily, even the earth. So a gamma ray wouldn't hurt you because it's going to pass straight through. It's just too strong. X-rays are high energy that pass through some solids. And these are the ones that take pictures of your bone, because the bone is enough to stop them. It's heavy enough. Lead will totally stop them. So X-rays can't go through the earth like gamma rays. Okay, alpha particles have a mass of 4 AMUs and a 2+ charge. They are deflected towards a positive pole, deflected toward a negative pole, because they are positive. Okay, and these end up being helium nuclei. We'll get to nuclei in just a few, but that's the other name for alpha particles. But they are positive, so they go towards a positive. Whereas beta particles have little mass. They do have mass, but not much. They're negative charge. And what they really are is high energy electrons. And much like the alpha particles are deflected towards a positive pole, okay, beta particles are deflected towards a negative pole. A positive pole. What I write and what I say here. Okay, beta particles are negative, so they go towards the positive pole. Alpha particles are positive, so they go towards the negative pole. So they used these different types of radiation to work on the atomic structure. And so this combines them, and they were able to use them. Gamma rays just go straight through. They're not deflected because they're not particle. If you'll notice, these are the betas and these are the alphas, and they're deflected. So they basically use these, since they are on the atomic scale, they were able to use these to hit particles in an atom. Think of it as playing pool with equal size balls. Now, at this point in time, again, frame of reference, the prevailing model was what was called the Plum pudding model. and it was proposed by J.J. Thompson. There's no P in Thompson here. All right, now we're not English. Plum pudding is a traditional English Christmas dessert. You know, you stick in your thumb, pull out a plum. We don't do that. So I'd refer to this as like the chocolate chip cookie model, because what we have here is the protons and the neutrons are all mixed up like cookie dough. So they're not individual particles, they're just all over the place. And then the negative electrons are the chocolate chips. In the case of the plum pudding model, they would be the plums. So in the chocolate chip cookie, they are the chocolate chips. So you have them dotted all throughout the atomic shape. Now, most of y'all are looking at this going, really? We know this. Yes, you know this now, but remember, this is at the turn of the 1900s, and they didn't know. So again, you've got to understand things in context. So Rutherford came along, and I told you he was playing with the alpha particles. Well, what he started doing was shooting the alpha particles through a very thin gold foil. Well, think about it. If this is a cookie, it's just going to like dig holes. If you're shooting at a cookie with a BB, it's just going to shoot holes through the cookie, right? Because the dough isn't really going to stop you. Well, what actually happened was yeah, some of them came through here, but a lot of them deflected. There were even a few that went straight back. And this freaked them out, because if you look down here at this interpretation, what you're seeing is most of them go straight through, but if they hit this nucleus, then they'll come flying backwards, either straight back at you or at an angle. Okay? So up here is where they show it actually hitting the nucleus, and it starts spinning off in space. So what that told them was that chocolate chip cookie isn't going to do it. Okay? So what Rutherford came up with was, he says, okay, this didn't work. So the atom is mostly empty space. We know that because things went straight through without any deflection, any holes in the particles or whatever. And so it's mostly empty space with the negatively charged species circling. Circling the nucleus. Okay? So the nucleus is a new idea. So what's a nucleus? So it has a dense, positively charged, and it has to be positively charged because the alpha particle was positively charged. So in order to get the best impact, it has to be positively charged central body that he's going to call the nucleus. So this is the nucleus. All right. And he went forward to say protons are the positively charged species in the nucleus. So now, remember, we have the electrons circling, and now we have the nucleus in the center. Okay? So the positive charge is carried by protons. The negative is carried by I'm thinking ahead, electrons. No, neutrons. That's what happens when you read ahead. in 1910, the atomic number was found to equal the number of protons in a nucleus. More about this later, but that's how the periodic table is arranged. Number of protons in the nucleus of a given atom. So if you have a different number of protons, you have a different atom. And in 1932, James Chadwick discovered neutrons. Now, the importance of this is multiple because they knew that there was something missing because electrons really don't have any mass. And they knew the mass of a proton, but it didn't account for the mass of the atom if you accounted for the protons. So there was some mass missing, but they knew it wasn't charged. And so James Chadwick, and this was 1932, so we're not even at 100 years for this one yet, discovered this. He was an American. This was one of the first Americans to win a Nobel Prize. And he was able to determine the proton. The proton was difficult to capture because there was no charge to it. They could work with it if there was a charge because they could attract it or repel it, etc. But because it's neutral, it doesn't play well with others. So Chadwick, it took a long time for him to prove it. All right. So if we look at our little chart, so protons and neutrons are in the nucleus. And so electrons circle, well, if I could spell a circle around the nucleus. And you're looking at a very, very small number. This is the number of angstroms. And an angstrom is 10 to the minus 10th. This is not one of the ones that you have to know, but know that atoms are very small. Now, the other thing you need to know is basically this is a mass of 1 AMU, this is a mass of 1 AMU, and we don't count. Because this is so small, this is like having a penny compared to a $10 bill, money-wise. So, yes, it does have a mass, but it's not critical. Okay, so this allowed them to ID all the species in an atom. So if we go back to the atomic models, the first one, remember, was the plum pudding. And that was where you have the electrons randomly distributed in a cloud of protons and neutrons. A cloud of protons and neutrons. Okay, and remember that was the plum pudding model, but I called it the chocolate chip cookie because we don't deal with that. So that was a reigning model for a long time, just like the Big Bang Theory is the new reigning model. There was a theory before that, and there was a theory before that. Ernest Rutherford came along and disproved that. So he came up with the nuclear model. And that's where the electrons randomly orbit a positive center, which we call the nucleus. Now, this is closer to what we do, the model that we use, but the actual model we use is Niels Bohr's model, which is the quantum model. Quantum. So, Quantum. It's a better spelling of it. And what it is this is the accepted model, and it works the same way as Rutherford's, but the electrons are in set orbits around a positive center. Okay, so Rutherford took it to the nuclear, and then Niels Bohr took it a step farther and said, wait a minute, these aren't random, this is a set system. So at this point in time, what we have done is been able to identify the pieces, parts within an atom and how they're arranged and how it goes into the structure. And again, a number of y'all are like, yeah, right, we've been there, done that. That's true. You know this model, but this is actually a new model. It's really not 100 years old yet. So what I need you to do is just think in the time frame where we're at. Now, in the next part, we're actually going to go into identifying the pieces, parts of a particular atom. So we're done with the intro to the model.